Hi guys, and welcome to this, my lesson on fitting a least squares regression line to numerical data. Oh, these titles get longer. My name's Darren from Maffs Guru. Thanks very much for joining me. Hopefully you're going to find this important and useful and entertaining. Maths entertaining. But before I go any further, can you do me a favour and subscribe to my YouTube channel? Follow me on TikTok, do whatever else you need to do. But by doing one of those, you actually let me know, and by that I mean subscribing to YouTube, you actually let me know that people are watching. All right? Please, if you can, that'd be greatly appreciated. Now, I always start with learning objectives, and this is the first part of this particular module of work, but it's building on stuff we have already done, and there are videos on maffsguru.com with downloadable notes that you can help you. Absolutely free to sign up. What are we going to do? Be able to define linear regression, be able to define what a residual is, introduce the least squares line of best fit, to be able to find the equation using summary statistics and technology. Now, obviously technology is really, really important here. And as I say, this is the first lesson of this course, but the whole of general maths requires the use of a CAS calculator. Yes, I put the class pad up there, the TI Inspire up there. I know there's the class pad. I try and use it as and when I can, but generally the functionality is pretty similar. But the work we're about to do will feature prominently in SACs. In fact, in many cases, I know SACs will have a good quarter of their content will be doing what is in this chapter. So being able to understand what to do, how to do it, is going to help you do really, really well. But you've got to know how to use your CAS really well. Now, what is linear regression? Now, we've noticed from previous lessons that when I plot numerical data versus numerical data, then we get a scatter plot, don't we? Yes, so All right, so I may plot some data, height against weight, I don't know, height against IQ, all those type of things could be related together. And what we notice is that there's probably some sort of relationship between that data. It seems to be stretching up, such that as when whatever's on the explanatory variable goes up, the response variable seems to go up as well. So there's some sort of link, and sort of age and height would be a most obvious one, up until sort of about the age of 18. Now, the whole point of linear regression is to say, well, can I fit a straight line through this data that will allow me to predict for values I don't currently have? And you're going to say, huh? Well, if I look at this number here, whatever this is, say this is my age, and say that is my height. I don't currently, if I project this line up, I don't actually have any of these blue dots sitting on that line. So I can't actually say with certainty what the height will be at age, right? And again, we are using this to predict, but what I can do is if I somehow manage to come up with some sort of line of best fit, I can now say, well, using my line of best fit or my linear regression line, I can now predict that this age here will have that height there. So we are using linear regression to predict. And if you wonder why I just made a silly mistake, a silly face, I've just banged my foot. My apologies. Right. The form of a regression line. A regression line is a straight line. I just drew one on the graph. And so it would make sense that we would have the equation of a straight line, wouldn't we? Y equals mx plus c. It might make sense, but no. Why? Because it's general maths and Barry's been at it. And if you don't know who Barry is, don't worry about it. He really should not be allowed out of rooms. So a linear regression line does not have the equation y equals mx plus c. It has the line or the equation y equals a plus bx. Huh? What on earth is this A, and what is the value of B? Well, believe it or not, all we've done is we've swapped around the y equals mx plus c, and we've created different letters. So, as we have known before, the value of A is my y-axis intercept. So we actually write that first, and the value of B is the gradient, or interestingly now, we call it the slope, because later on we're going to interpret the slope. So it's going to be important to notice that whenever you write a linear regression line now, it's got to be in the format y equals x plus bx. But you are never going to write the letters y and x. And sadly, this is a huge trick. Don't write the letters y and x. So let's just explain what it is. And you're going to turn around and say, why are you telling me this? And I'm going to turn around to say, because that line there has been in an exam. Right? Don't think they're just going to ask you to work out maths stuff. They're going to ask you to understand it, right? If you want a 50, you want to do a 40 plus, you've got to absolutely understand this stuff, not just regurgitate it. So it's best to explain the least squares line is a line that minimizes the sum of the squares of a residual. So thank you, Cambridge, for allowing me to use your examples. You guys rock. Really, really helpful. But what do we notice here? This distance here, the distance between this regression line, all right? So this here is a suggested regression line. It might not be the regression line, it's a suggested one. But here we've taken sort of some way of drawing a line between those points. And then what we've said is, well, let's look at the distance. Each of the points now have to the line. So we look at the vertical distance. So this is a vertical distance. Here is my point. Here is my prediction, right? And again, remember that my line here are just predicted values. So here is a prediction. There is a line taking it from my actual point to my prediction. I've got a point here. There's my prediction. There's my actual point. Here is my actual point. There is my prediction. So it would appear that some of the points, some of the actual points fall above the prediction, and some of the actual points fall below the prediction. Okay, we'll come back to later. But what we now need to know is that these differences, those distance there, are called residuals. And a residual is really, really important. So what the calculator does is it works out for any given regression line, it works out all of the distances the points lie from that line, and it says, well, okay, I'm now going to sum the square of all those differences, right? I'm going to square all of these differences and I'm going to sum them together. And what it tries to do is find a line that has the smallest square of the residuals. That's really important. Now, we've got information here or language here that's important. A positive residual is when the actual point lies above the line. A negative residual is when the actual value lies below the line, and a zero residual is when the point lies on the line. And that can actually happen. We can have points on the line. Residuals are going to come massive a little bit later on. Now, when you fit a least squares line, again, this is absolutely SAC information and exam information. I've seen this over and over again. There are three assumptions that we make when trying to do a least squares line. All right, three assumptions. The first one is the data is numerical. It's got to be numerical, because remember, to draw a scatter plot, you can only do numerical data versus numerical data. The association is linear. We cannot fit a straight line to a curve. Your calculator will try and do it because it doesn't know any better. But if we have data that is curving up, we can't, because a straight line, a least squares line, has to have data going in a sort of linear fashion, and that there are no clear outliers. This is the one that most people forget in an exam. If there are outliers, it's going to mess things up massively. But anyway, we'll see that in a little bit later on. Now, finding the equation of the least squares line, obviously there is a CAS enabled to this, and that's coming up a little bit later on. But there are equations, and there are ways of finding this. So if we go back to my equation I had a moment ago, where we had y was equal to a plus bx, there are ways of being able to find the value of a and b. So here is my value of b, and to find the slope, which is b, I do r sy over sx, r times sy. I wouldn't know if this is sy. In fact, what is r? Well, if you remember from previous video, r is my correlation coefficient. What is this sy and sx? The standard deviation of the y values, the standard deviation of the x values. Now, these will either be given to you, or if you are really, really unlucky, you'll have to work them out. To find the intercept, that's our a value. So this a value here, we have to do y bar minus bx bar. Oh, hold on a moment. We've already got the value of b. So here is my value of b, which we will obviously be substituting into there. But what is this y bar x bar business? Well, we've met x bar before. X bar is basically the mean of the x values, and y bar is the mean of the y values. So there seems to be a lot of working out there, doesn't there? And for your summary book, that is also important. In many cases, they'll actually ask you to find the value of r, right? So in that situation, they will give you the slope, they will give you sx, and they will give you sy. In fact, they may give you the slope by writing the equation out. There's lots of ways that they can try and trick you, but I have seen this over and over and over and over and over and over again. All right, so let's look at an example. The height and weight of 11 people have been recorded, and the values of the following statistics determined. Now, again, whenever I see this in an exam, I know that it is trying to help me work out, you know, when I see this, I know what I'm going to be doing. I know it's those formulas I've just been dealing with. Use the formula to determine the equation of the least squares regression line that enables weight to be predicted from height. Now, again, the language there is really important. When it says predicted from, that is going to be my EV, weight to be predicted from height. So in that situation, if I draw a very quick diagram, weight is being predicted from height. So we've got to make sure we get those the right way around. So my SY value is going to be weight and SX is going to be height. Right, what do we got here? So Y is equal to A plus BX. So the first thing we need to do is work out the value of B, which is R times SY on SX. I'm just going to go back and check I've got that right. SY on SX. And again, you've got a summary book that you can write this down. So what is the value of R? That is my correlation coefficient. And they've given that to me in the table here. So I know my B value now is 0.8502 times SY. Now you'll notice here they haven't actually given you which one's SX and SY because you've got to guess. So my Y values are here. So those are my Y values and those are my X values. My height, let me just check this. It enables weight to be predicted from height. Yeah, this is it. So weight's got to go there. So my weight is my Y. So SY, I'm looking for the standard deviation of my Y values, which is that there. So that's going to be 7.594 divided by SX, the standard deviation of X, which is going to be 7.444. Can't do that in my head. So I basically fire up my calculator, which is annoying because it's all over my working out. Sorry about that, guys. I will fix that in a moment. So 0.8502. I'm going to multiply that by 7.594 and divide that by 7.444. Hit enter and out comes 0.867. Now it says rounded to 2 decimal places. So again, don't forget the accuracy that we've got to do this to. So my value of B then is going to be 0.87. Have I finished? No, because I've got to work out the A values now. So if you remember, my A is given by, and let's just check, Y bar minus B times X bar. Y bar is the mean of my Y values. Well, we know the mean of my Y values, again, is now 65.45. So 65.45 minus B, well, we just worked out what that value of B was. It was 0.87. So 0.87 times my X bar values, which is 173.7. Let's just move this over for a moment so that I've actually got some space to work on. And then again, fire up my calculator to help me work that out. So 65.45 minus 0.87 times 173.3, he says. Let's make that 3. Hit enter and out comes minus 85.32. Have I finished? Nope, because I have to now do my regression line. And again, this is where lots of people mess up these particular questions, sadly, and that's because they don't write it correctly. I know the formula is in Y equals A plus BX, but you have to write the Y as what it is. You have to write the actual words in. So in that situation, we can say that my weight is equal to, what is it? A minus 85.32 plus B 0.87 times X, which is height. Again, sorry about my handwriting. So this here is my intercept. Here, that 0.87 is my gradient. That means for every 1 unit of height, I gain 0.87 centimeters of height, okay? And there we go. So that comes up over and over again in exams. Use the CAS to find and graph the equation of the least squares regression line. Okay, CAS that makes this so much easier. And again, for your ClassPad guys, it's very, very similar. All right, so the first thing I'm going to do is I'm going to put height. And I'm going to put weight. Now remember, you always put the things in there. And the interesting thing that they've actually told you here is they've told you what your EV and RV is. So they've told you let your height be your X and your weight be your Y. All right, so let's see what we come up with. Put the data in: 177, 182, 167, 178, 173, 184, 162, 169, 164, 170 and 180. Now, how many data items are there? Are there 11? There are 11 people. Scan up just to make sure I've not done anything silly or obviously silly. 74, 75, 62, 63, 64, 74, 57, 55, 56, 68, and 72. There we go. Right, now to find and graph the equation of the least squares regression line. Lots of ways of being able to do this. First thing I can do is I'm actually going to put my thing in there. So I'm going to go Menu, Statistics, Stat Calculations. And again, because my calculator is really sensitive, what you'll notice I've got two variable statistics. That's certainly one thing we can do. I've got linear regression, A plus BX. Doesn't matter which one you use. I tend to stick with linear regression A plus BX, and I'll show you why. So when I do that, my X list is, well, what's on my X list? It is height. What is my Y list? It is weight. When I click on OK, I get a load of information. I get A, B, R squared, R, ooh, hold on, A of, and B. What are these A and B values? Well, we know, we actually already have you. So I can actually take that information out and straight away write that therefore my regression line is, remember, it is Y equals, not Y equals. We've got to write the actual wording. So it is weight is equal to my A value, which is minus 84 point. Now it says to 3 significant figures. They're trying to trick me here. And lots of people struggle with significant figures. If you do, you've got to get this right. So 3 significant figures, you start counting from the first digit. So in that situation, it would be minus 84.8. And then what have I got here? I've got to do plus my B value to 3 significant figures is going to be 0.867 times my X value, which is height. And there we go. That's my linear regression line, right? That's certainly one way of doing it. What else does it want me to do? And graph it. I'll show you how to graph it in a moment. But that looks suspiciously like the one we just dealt with a moment ago. Minus 84.8 and 0.867. Okay, so now let's show you how to graph it. To graph, I'm going to do Control and Doc. And I'm going to add data and statistics. And what you notice is that my calculator just puts random dots. If you're doing this, your calculator won't look like that because it just randomizes it. It says down here to click or enter to add a variable. So I'm going to click. And what is on my X axis? It is height. Oh, pretty animation. You'll see that it also says on the right, click to enter a variable. I want weight. And there we go. Now what we notice is that there is some sort of, I can't actually draw on this unfortunately guys, but we notice that there is some sort of sloping up of my data. And now how do I do my linear regression? Well, funnily enough, I go Menu, Analyze, Regression, Show Linear, and A plus BX. Now I know there's linear MX plus B, but we always use the A plus BX. And you'll notice, once again, there is my equation. Now the calculator is not clever enough. It starts with Y equals. It should start with weight equals. But again, if we were rounding that to 3 decimal places, we'd have minus 84.8 plus 0.867. Ka-ching, ka-ching, ka-ching. All right, job done. So there we go. That's how to use the CAS. And that's going to come in handy all the way through. Okay, so moving on to some VCAA questions. Oscar has walked for 9 consecutive days. The time in minutes that Oscar spent walking on each day is shown in the table below. Okay, a least squares line is fitted to the data. That's giving me a hint as to what I'm going to do. The equation of this line predicts. We've got to come up with an equation to predict that on day 10, the time Oscar spends walking will be the same as. All right, so first things first, got to fire up my calculator. So let's do Menu and List and Spreadsheet. So what do we got? We got day and we have time. So making sure we put our data in accurately, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then what have we got here? We've got 46, 40, 45, 34, 36, 38, 39, 40, and 33. Just skimming back up to make sure I've not made any obvious errors. There we go. So I need a least squares line. Easiest if I go Control, Doc, Data and Statistics. We'll have day on the bottom and time up the side. And then what we have, menu, analyze, or regression, a plus bx. Move that up a little bit and there we go. We have a nice equation. Now we don't want to write the y and x because that's stupid. So what have we got on the y? So we've got time is equal to 44. They got this plus minus. That's because the calculator doesn't really know what it's talking about. But we know a plus and a minus is a minus. 1 times x, which is the day. So basically, 44 minus the day is going to give me the time. Job done. Right, let's see. So the equation that lines predict. So we're looking for day 10. So for day 10, the time is going to be 44 minus 10, which gives me 34. So which day has 34? Which day took 34? It was day 4. And so B would be my correct answer. A nice easy question to ease our way in. Then we get to this one. The table below shows the weight in kilograms and the height in centimeters of 10 adults. A least squares line is fitted to the data. Oh, here we go again. Least squares line. The least squares line enables an adult's weight to be predicted from their height. Okay, so weight is being predicted from height. Useful to know. The number of times that the predicted value of an adult's weight is greater than the actual value. So the predicted is greater than actual. So if this is my prediction, and that's always got to be greater than my actual, then my actual points have got to be down here, which means I am looking for, well, either points below that line or negative residuals or whatever. Okay, so again, let's fire up my calculator and see what we can do. Let's clear down what we had on there earlier. Nope. Let's put in a list and spreadsheet. What have we got here? We've got weight and we got height. So I'll put the numbers in, and having put all the data in, I'm just going to scan up to make sure that it all looks reasonable. It does. All right, so we've got to fit a least squares line. So Control, Doc, Data and Statistics. Along the bottom is height, up the side is weight. All right, so menu, analyze, or regression, linear A plus BX. Right, so basically we want to know how many of those dots fall below the line. Yeah? Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 dots. And I always worry that some of the dots sit on top of each other. But in this situation, there are 10 dots that I can count. I'm looking for the ones below the line. 1, 2, 3, 4, 5, and 6. So it would appear that there are 6 dots. So I will select D as my correct answer. There is another way of doing this. We could actually go menu, analyze, residuals, show residual plot. And again, count the ones that fall below the line. And I like this better maybe because that dot that I'm highlighting, the 180, minus 1.14, basically is giving me an indication that there it isn't on the line. Whereas on the graph here, I might be going, oh, is it on the line? Is it not on the line? Is it on the line? I don't know. All right, so there we go. Next one, the least squares line of the form y equals a plus bx is fitted to a scatter plot. Which of the following is always true? The trick here was the words always true. All right, let's see. As many of the data points in the scatter plot as possible will lie on the line. That's rubbish. All right, not possible at all. The data points in the scatter plot, I mean, it might be possible in some lines, but not all the time. The data points in the scatter plot will be divided so there are as many data points above the line as there are below the line. Well, I don't know about you, but that used to be what I did back in year 4 when I used to have to do lines of best fit. So, no, that's not a least squares or a least squares line. Oh, the sum. Now, you notice about C, D, and E, the wording is very, very similar. The sum of the squares of the shortest distance from the line to each point will be a minimum. Now, if this was my regression line, and this was, for example, a point, believe it or not, the shortest distance is actually perpendicular to the line. Well, we haven't learned anything like that, so that basically can't be it. So it can't be C. The sum of the squares of the horizontal distances. The horizontal distance from the point to the line. Well, we haven't dealt with anything horizontal distances, but it is giving me an indication of the fact that it's actually the sum of the squares of the vertical distances. Because if you remember, the vertical distances are our residuals. So in that situation, E would be the correct answer. And what you notice is that has nothing to do, we didn't do maths, that was testing our understanding. Did we understand what that question was all about? A study was conducted to investigate the effects of drinking coffee on sleep. In this study, the amount of sleep in hours and the amount of coffee drunk in cups were on a given day were recorded for a group of adults. Now, when I see summary statistics, I automatically suggest or know that it's going to have something to do with y equals a, what is it? Oh, I don't know, we've got a square there. Y equals a plus bx, where we know that b is equal to r times sy on sx, etc. So there's going to be all that stuff. And again, if you've got it in your summary book, awesome. All right, the following summary The following summary statistics were generated. On average, oh, now that's going to tell me about a slope maybe. On average, for each additional cup of coffee drunk. Now, if that there is telling me that the amount of coffee goes on there, and sleep goes up there. So sleep is my y and coffee is my x. And the reason that's going to be important because I want to know my sx and sy. On average, for each additional cup of coffee drunk, the amount of sleep, or basically they want me to find the gradient. That's effectively what that is. And the gradient is the value of b, and b is found by r times sy all divided by sx. So my value of b is equal to r, which is minus 0.770, times sy, where's sy is 1.12, divided by sx of 1.56. Fire up my calculator. Tie my kangaroo down. There we go. So let's do that. So we've got, I have to do the minus sign, or my calculator gets a bit upset. 0.770 times 1.12 divided by 1.56. Hit enter. And we get a gradient of minus 0.5528, etc., etc. Well, minus is decreasing, so we're looking for a decrease, and the only one of 0.55 is in fact A. So A would be my correct answer. And there we go, that's the end of this video. Hopefully it has been useful. Remember, it's not just about learning the maths, it's about understanding and applying it to a range of different questions. That's where practice really does make perfect. There are other videos in this series. Thank you very much for watching this one. Hopefully I'll see you in another. If not, please take care and stay safe.